Hello everyone. So in this video we're going to talk about how do we use z-table to find normal event probabilities. Previously we used the empirical rule to find the normal probabilities, the 68, 95, and 99.7% rule. But that rule is very limited in use. You can only use that rule if the normal event is bounded by the 7 marks of a normal distribution, which are mu plus or minus 1 sigma, mu plus or minus 2 sigma, mu plus or minus 3 sigmas. If a normal event is not bounded by those 7 marks, you're not able to use the empirical rule to find the probability anymore. But by the approach of z-table, there's no limitations. You can use z-table to find any normal event probabilities. And today we're gonna, in this video, we're gonna demonstrate how. So first, we need to understand what a z-distribution is. So we know for normal distribution, we have two parameters, mu and sigma. Mu can be any real numbers. Sigma can be any positive real numbers. So when you vary mu and sigma, the combination, we can have tons of different normal distributions. We have a different parameter. Out of all the possible normal distributions, we're going to define one special normal distribution. And that's our z distribution. So z will have a normal distribution where population mean mu equal to 0 and the population standard deviation sigma equal to 1. And that's our standardized normal distribution. We call z a standard normal variable. Okay, so in reference to regular normal variable x, here is standard normal variable z. Okay, so keep that in mind. Now let's look at the structure of the z-table. So with the z-table, we can find probability of any event in z distribution. Okay, so first we're able to deal with z distribution. So in z-table, we have two sides of the tables, and they have exactly the same structure. The print on the table is very small, so if you can print a z-table out and as a reference, that will be very helpful, so that you can understand the examples that give from the video here. The z-table is provided to you as a link, a PDF file from Canvas, so you can download and print. So in the z-table, the first column on the top row will give you the z-scores. Okay? And the first column will give you up to the first decimal point of the z-score, and the top row will give you the second decimal point of the z-score. So, and all the negative z-scores are on the left-hand side of the table, all the positive z-scores are on the right-hand side of the table. Okay. So for example, if you want to read a z-score of negative 1.03, negative 1.03, so we're going to look for negative 1.0 on the first column, 0.03 on the top, that will be negative 1.03. Okay. If you want to read a z-score 0.93, you're going to find 0.9 here on the first column, and then 0.03 on top, so 0.93. Okay, so z-table has two decimal places for the z-score you read. And if you want to find a z-score with more than 3 decimal places, then you basically just need to round it to 2 decimal places. Okay. So then basically, when you look at the range of the z-scores, the z-table gives us all the z-scores between negative 3.49 to positive 3.49 with a step of 0.01. Right? So it covers the entire range from negative 3.49 to positive 3.49. And then for every z-score, it provides a probability values inside the table. all these 4 decimal point numbers, their probability. So the z-table basically gives us a one-to-one relationship between any z-score to its probability. Okay? So that's a one-to-one match, one-to-one relationship. And that relationship is displayed by the density curve on top of the z-table. So basically for any z-score that paired with a probability, the probability will indicate to the left of the z-score. Okay. So for example, if we find one pair relationship as a demonstration, so for example, we have a z-score of negative 0.63. When you look up in the z-table, negative 0.63, the probability paired with it will be 0.2643. So we have paired relationship negative 0.63 to p 0.2643, which means in the density curve, z equal to negative 0.63, p equal to the shaded area probability will equal to 0.2643. And if you write this relationship in a mathematical formula, basically what we get is probability of z less than negative 0.63 equal to 0.2643. Okay, so basically z-table gives us a paired relationship between z and p in terms of to the left of that given z-score. So that's basically the one single rule you need to remember in terms of reading z-table for probabilities. It's always give you to the left of any z-score probability. So we know to the left, in terms of mathematics, we're going to use a smaller than sign to indicate the relationship to the left, right? So basically, anytime if you look for probability of z smaller than a z-score, then you can look up the probability as is from z-table for the relationship. And if the sign is not smaller than sign, then you have to convert it into smaller sign. Then you can use z-table. Okay. So now let's look at a couple of examples here. So for example, if we want to find the probability of z smaller than 1.31. Okay. So we can see the sign smaller than sign, which is consistent with the relationship on the z-table. Then we can just look up as is. We can look up the paired probability values with 1.31 on the z-table. So we can look for 1.3 and 1. So the probability is 0.9049. That will be the probability of the event of z smaller than 1.31. So for any probability with a z event with a smaller than sign, look up as is, and that's it. Okay. What if we're trying to look for probability of z, a different event, a z greater than 1.31? So what if the sign is greater than sign? So it's not consistent with the z-table. Then we have to make changes. We have to transform it. So the easiest way to understand the rules of the transformation will be through the density curve. So if we write this, if we use density curve to represent this event, you have a standardized normal distribution, z distribution, center at 0. 1.31 will be somewhere to the right of 0, 1.31. Since the sign is greater than sign, you're looking for probability or area to the right of 1.31, right? So this probability will be the entire density curve distribution. So the entire probability for the entire density curve, subtract the probability from 1.31 all the way to the left. So basically this small area on the right tail will equal to probability of the entire density curve subtract the probability to the left of 1.31, right? And then from the density curve, we can write to the formula as, so the entire density curve probability will equal to 1, right? There's 1 with the probability rule. Probability of the entire sample space equal to 1. So the total probability under the density curve will equal to 1. And then this probability can be represented as probability of z smaller than 1.31, right? It's to the left of 1.31, so that would be smaller than. And the sign in the middle is a subtract sign, right? So we 1 subtract this. Then we can see probability with a greater than sign event is transformed into 1 subtract the probability with a smaller than sign. And we know for the smaller than sign, we can look up the probability as is, right? So we can say this will be 1 subtract, and that probability equal to 0.9049 as we looked up previously. So we can do the math, will be 0.0959. So that's the probability of z greater than 1.31. So anytime you have a greater than sign, basically you need to use the z-score, look up probability, then subtract that probability from 1. Okay. And then in z-table, the events could be like z between two z-scores. So for example, between 0.2 and 0.8. So if we draw the intensity curve, it will be symmetric bell shape, center at 0 as our z distribution. 0.2 somewhere to the right of 0, 0.8 further to the right. We're looking for the area between 0.2 and 0.8. Okay. So we can also transform this probability or transform this area as difference of two areas. So for example here, if from 0.8 all the way to the left, subtract probability from 0.2 all the way to the left. So intuitively, this slice area in the density curve will be from 0.8 all the way to the left, subtract from 0.2 all the way to the left, right? Then we're going to write each of the density curve in terms of the event. This will correspond to probability of z smaller than 0.8, and this will correspond to probability of z smaller than 0.2, right? Then the sign in the middle is subtracting, right? We're going to subtract them. And then probability of z between two z-score are transformed into the difference of two events with both event with a smaller than sign, which we can use the z-table to look up, right? So then we go to z-table. 0.8 will give us probability of 0.7881. 0.2 will give us probability of 0.5793. So we just need to subtract them, use a calculator. So 0.7881 subtract 0.5793. We do the math as 0.2088. Okay. So that's the probability of z between two z-scores. And basically, the three different events basically covers all the possible different ways of looking at probabilities in z distribution. Either you have a smaller than sign, or greater than sign or between two z-scores. Okay. In conclusion, if you try to look for a probability of z smaller than a z-score, you're going to find the paired probability with that z-score on the z-table as is. No change. That's it. That's the relationship the z-table gives you. If you try to find the probability of z greater than a z-score, you need to look up the probability with the z-score provided on the z-table, then subtract from 1, as demonstrated by the relationship here. So 1 subtract the probability of the z-score that you have when the sign is greater than sign. Then when you have z bonded with two z-scores, then you need to find the probability for each z-score, then subtract them. Use a bigger probability, subtract the smaller probability. And that rule is demonstrated by the density curves here. Okay. So that's all the possible ways of finding probability using z-table. Okay. And now, what if we have a regular normal distribution? How do we find the probability for a normal distribution that's not z, but x? Okay. So keep in mind, we can do transformations from x into z by a relationship z equal to x minus mu divided by sigma. So once you understand how you find the probability of z, then find the probability related to x, all you need to have a one extra step. So convert x into z using z equal to x minus mu divided by sigma. Okay, so for example, let's look at this. So if we want to look for, if we have a normal distribution x with mean of 100 and sigma equal to 10, so that means this is mu, this is sigma. If we want to find the probability of x greater than 125, how do we do it? So keep in mind, we need to standardize into z by z equal to x minus mu divided by sigma. So in this case, this probability can be standardized as, we're going to keep the sign as is, and then on both sides, we're going to perform this z transformation. So on the left hand side, we use x minus mu. Mu is 100 divided by sigma. Sigma is 10. And then on the right hand side will be 125. Subtract mu, 100 divided by sigma, 10. So then this event is converted into x minus mu divided by sigma, that's z, greater than, and here we can calculate the z-score. So 125 minus 100 is 25, divided by 10 is 2.5. So this event is equivalent to this event. And all we need is find the probability of this event, right? So from previous demo, we can see this will be 1 subtract probability of z smaller than 2.5. Then we can look up in the z-table with 2.5. If we look up at the z-table, we got 0.9938. So we do the math, 0.0062. So that's probability of x greater than 125 when x has a normal distribution with mu equal to 100 and sigma equal to 10. Okay. And for any other normal distribution, likewise, you can do the same thing. For example, if x has a normal distribution with mu equal to 40 and sigma equal to 5. So this is mu, this is sigma. How do we find the probability of x smaller than 43? Okay. So then we standardize. We're going to keep the sign as is. Then x subtract mu divided by sigma. Then 43 subtract mu divided by sigma. Right? Then that will be probability of z smaller than we calculate z-score will be 3 divided by 5, it will be 0.6. So here you can see the sign is smaller than sign, then we don't need to do anything extra, just find the paired probability with 0.6, right? So 0.6, when you look up the z table, that's 0.7257. And that's it. We're still going to use this distribution. What if we try to find the probability of x between 35 and 43, for example? That will be probability of. So now we have 3 parts to standardize. We're going to keep the 2 signs as is. In the middle will be x. We're going to standardize x by subtracting mu divided by sigma. Then on both sides, we need to standardize the same way. So 43 minus 40 divided by 3 divided by 5. And then here will be 35 minus 40 divided by 5, right? So this will become probability of, keep the sign as is. The middle part will be x minus mu divided by sigma. That's our z. On both sides, we can calculate the z-score. So here, we got -1. Here, we got positive 0.6. And from previous demo, this will be probability of z smaller than 0.6 minus probability of z smaller than -1. Right? So we look up the z table. For 0.6, smaller than 0.6, probability is 0.7257. Subtract probability of z smaller than -1, the probability will be 0.1357. Okay, and if we do the math, it will be 0.5900. So that's the probability. So you can use calculator to calculate it. Okay. So then with z table and the standardization formula, we can find probability of any normal events. Okay. And a lot of times we're going to have word problems. So for example, we have a word problem like this. The length of time for a college achievement test is found to be approximately normally distributed, with mean of 75 minutes and the standard deviation 15 minutes. So basically, out of all the students who take the test, their average time is 75 minutes with standard deviation 15 minutes, and we can assume this is a normally distributed. Okay. So if you use x represent the length of time for a single student, then we can see x is normally distributed with mu equal to 75 and the standard deviation equal to 15. So mu and the sigma. Okay. Then for every problem, they're asking you proportions or probabilities. Basically, you're trying to find the probability of a normal event. So for example, first, what proportion of students who take the test will be able to finish within 60 minutes? So we're basically looking for probability of x smaller than 60, smaller than or equal to, right? And in normal distribution, when you have events has equal to or not have equal, has equal sign or not having equal sign, it doesn't make much difference. Doesn't make any difference in terms of probability. Okay, so basically looking for a probability of x smaller than 60, where x has a normal distribution with 75 and 15. So that go to the previous example. We need to standardize the event into z, then look up on the z table. So let's go ahead and do this. That'll be probability of, we keep the sign as is, and x minus mu, 75, divided by sigma, 15. And here will be 60 minus 75 divided by 15, right? So the front part, this will become z. And here we have 60 minus 75, that's minus 15. Negative 15 divided by 15, that'd be negative 1. Then since the sign is smaller than sign, it's consistent with z-table, so we can look up directly from z-table. For negative 1, the probability is 0.1587. So that would be 0.1587. Okay. So about 15.87% of students will be able to finish within 60 minutes. Question number 2, what proportion of students will take the test will take more than 120 minutes to finish? So then we're looking for probability of the time student take will be higher than 120. Okay. So then again, we need to standardize the regular normal event into z. We need to standardize x into z. So we're going to keep the sign as is. Then x minus mu, 75 divided by sigma, 15. Here we're going to have 120 minus 75 divided by 15. So probability of z greater than, so we'll do the math, 120 minus 75, that's 45. When you divide it by 15, that will equal to 3, right? So when you look at the sign, this is greater than sign from the previous example. This will be 1 minus probability of z smaller than 3. So when you have smaller than sign, you can use z-table. With smaller than sign, we get 3.9987. So 0.9987. If you do the math, 0.0013. Okay, so the answer will be 0.13% of the students would take more than 120 minutes to finish. Okay. And next question, what proportion of the students who take the test will finish between 50 minutes and 80 minutes? So basically looking for a probability of the time between 50 and 80. Then we can standardize the event using z equal to x minus mu divided by sigma. Mu is 75, sigma is 15, right? And 50 subtract 75 divided by 15. This would be 80 subtract 75 divided by 15. So we can calculate z in the middle, and then we have two z-scores. So 50 minus 75, then divided by 15. We got negative 1.6666, a lot of sixes. So we need to round it to 2 decimal places. So negative 1.67. Okay. And the other side will be 0.33. So also round it to that 2 decimal places. Anytime you calculate the z-score, round it to 2 decimal places. Then from previous example, this will be probability of z smaller than 0.33, subtract probability of z smaller than negative 1.67, right? Now the sign are both smaller than sign, we can use z-table. So 0.33, that will be 0.6293. Subtract negative 1.67, probability will be 0.0475. And if we do the math here, 0.6293 minus 0.0475, we got 0.5818. So this is basically how we use z-table to find any normal event probabilities. And also we can solve some application problems. Thank you for watching.